Okay, take a seat, please. Before we start with our talk today by Eric McFarland, I want to bring to your attention that there will be a seminar on Friday, 2 p.m., LA 1605, and the speaker will be Simon de Lyon-Levis, who's chief scientist at the French Atomic Energy Commission. But he's working on nanoelectronics, especially looking at extending Moore's law by working with three-dimensional structures. Should be an interesting talk. That's at 2 o'clock this Friday. Today, Eric McFarland, whom I think you all know, probably better than I do, because you've been here longer than I have, is going to talk to us about solar production of electricity and fuels. Is there a cost-effective path forward? And Eric, who I'm sure, as I said, is known to most of you, I took a look at his bio, and what I hadn't appreciated is this guy's really a bit of a Renaissance man. He's not only got undergraduate degrees and master's degrees in nuclear engineering, and then PhD from MIT, but he also has an MD degree from Harvard University and has done an internship in general surgery, which I'm sure is very useful in his current work. Maybe he'll tell us about that. But his main research area, as most of you know, is focused on coupling fundamental chemical processes at surfaces with novel material systems, and especially for applications to the production and interconversion of fuels and energy. He's also involved in a very big and important project called JCAP, which in fact, he is UCSB's representative of this. This is JCAP is the Joint Center for Artificial Photosynthesis. It's a DOE hub, I think $125 million funding level over 5 years that is led by Caltech and Lawrence Berkeley Lab. And Eric mentioned he will just touch on that in his talk today. So please, Eric.
Well, I'm not going to talk much about JCAP. In fact, I'm going to talk about mostly the first thing that's important in energy production, which is money. So I appreciate the introduction. What I'm going to try to cover today, if this works, is a little bit on the big picture, because there's a lot of people here from different backgrounds, and the context in which people do solar energy conversion. I'll talk about what works and what doesn't and why they don't work. And then I'm going to talk a little bit about strategies and tactics about how one might convince people to pay for things that will develop possibly energy in the future. And then I'll talk a little bit about the work we do here at UCSB, depending on how much time I have left, and make a few comments about work beyond splitting water to make hydrogen and oxygen. So one thing I always like to start with is that to make sure everyone understands that thermonuclear radiation is why we're alive. And at the end of the day, sunlight is just the thermal radiation from the surface of the sun, powered by fusion. And this is always going to be the case. And whether we have reactors in distant places or on the Earth, this is the way it will always be. And whether we can make use of it indirectly or directly is a question for all of you all. Interestingly, until or through the 19th century anyway, we were pretty sustainable on an energy basis. We used wood primarily for getting us through the Industrial Revolution in Europe. Wind and hydropower, which are also solar-driven processes, were sustainable and economically proven by centuries of market economics. So these are things that work. And certainly human muscle up until the 20th century was a big part of how we did things. We were so successful at using these sustainable sources that they stopped being sustainable. And in fact, we deforested much of Europe and part of the Middle East in our quest to use wood, and that didn't work out so well. We also hunted things like whales, which we were using for lamp oil, not necessarily to extinction. That's a bit of a myth of why we stopped using whale blubber for lamps, but nonetheless, we took out a lot of whales. And we switched, and all of this was really a measure of our prosperity, if you will. And what's interesting is we really were a sustainable and renewable society through the 19th century. In the 20th century, what changed was they stopped being sustainable. It wasn't sustainable to use wood anymore. It wasn't sustainable to use water anymore. And fortunately, there was coal in the ground and oil that we could use that would match the prosperity that we had. And most importantly, the increase in population. We could certainly support a 2 billion person Earth with sustainable resources using technology we have today. But we don't have 2 billion people. We have 7 billion people. And so I always will say that the 22nd century is going to be one where we have to do something quite different than we do today. We'll probably need 32 terawatts as opposed to the 17 terawatts we need today. They'll probably be closer to 20 billion or 10 billion people in the 22nd century. And what we have to do in this generation that's here is figure out how to get us from where we are today to that point. And right now, it's not clear how that will happen. Like it or not, whether you think oil is good or not, it's the reason we have the lifestyle that we do. It's because we're prosperous because oil was cheap. And it's really that simple. If it weren't for oil, we wouldn't have the life that we have. And it's made egalitarian prosperity possible throughout the world. And that's just something you can accept. It's not really arguable. It's just a fact. Now that we are where we are, using oil as our prosperous fuel, we can now, as a planet, make $63 trillion. That's the GDP of the Earth, roughly. And the GDP isn't the best measure of what you create in terms of things, but it's not bad. And if you take our $63 trillion global product, if you will, and you look at how much energy we use to do that, it will give you a physicist-like basic principles. And here's the basic principle. We can't spend more than $120 per gigajoule, otherwise we're spending every single penny we make. And so there is a limit on how much we can spend on energy, even though people don't like to say that. And that's the number. So you can't really argue it. Now, people will pretend for short periods of time they can spend more than they make. And that is true for a short period of time, but not in the long run. So you have this conservation of money. And you can do that same little trivial arithmetic for different countries. You can do it for the US, Germany, China, India. You can look at their energy consumption. And interestingly enough, all those numbers are about the same. Germany is a little bit more. They can spend $190 per gigajoule if they spend all their GDP. And in China and India can both spend about $50 a gigajoule. And that's it. The upper limit. Can't spend more. Now, we know that that's not the case. And in fact, we can't spend all of our GDP. And if you go back even to the 1700s and you look at how much people spent on energy, their fire for their stoves and so forth, the wood, it was about 10 to 15%. It's always been that. There's even numbers from the Roman times, and that you can figure out how much the Roman soldiers paid for their oil and everything. And it works out, it's about 10 or 15%, never more. And in times of economic stability, that's pretty much a good number, and that tells you then how much we can spend on energy per gigajoule, about 10 to 15% of that maximum number, which turns out to be about between $5 and $15 a gigajoule. And if you spend more, like people want us to do, they want to raise the prices of energy, it means it has to come from something else. That's just a fact. And it will come from things like retirement accounts and education accounts for your kids. It'll come from somewhere else. You have to take from one to give to the other. And so how do we do that? Interestingly, that magic number of $10 to $15 per gigajoule has been true in times of economic prosperity over long periods of time. And if you put things like commodity foods, like corn, wheat, and rice, which are fungible products around the world, and you price them in any of the local currencies, over long periods of time, they don't deviate very much from that number of between $5 and $15 a gigajoule over long periods of time, hundreds of years, if you normalize the dollars, and that ends up being about 10 to 15% of their GDP. And looking at the prices back in 1980, for example, these were the prices of corn, wheat, and rice just before the economic upheaval. And oil at $85 a gallon is at about $14 a gigajoule. Interestingly, food and fuel have about the same value. So you could burn the corn and do okay thermally as a fuel. It's just we can't make enough of it. Now, bad things happen historically whenever these things change. And we saw it happen in the 1980s. We saw it happen in 2008. Whenever this magic number was exceeded, we saw significant financial results of responses to that price increase. And if you look today, that's happening again in many cases where the food and fuel prices are exceeding these limits. And what will happen next is anyone's guess. But it seems to be true historically that something bad will happen. So if we're going to think about sustainable energy, solar energy, where's the money going to come from? One thing that's interesting is how infrequently, when you have a conversation with people working in solar energy, where the money is expected to come from, it kind of escapes the conversation. But I think it's really important for young people working in the energy sector to be very aware of it, because many of the technologies that many of you are working on are less of a physics problem as an engineering problem to try to make these systems cheaper. So you have to know where the money comes from. It comes from banks, or the bank equivalent. And there's ways of valuing that cost of capital, cost to build your box that makes the energy, that are very well known. They're just as well known as the Quadratic Equation. So you guys can solve those things. You can solve these problems. And so if you take it as a given that energy has to cost around $10 to $15 per gigajoule, you can figure out then a relationship for how much this box of any kind can cost you. And it turns out when you go through the numbers, even if you borrowed the money from your mom, you have to pay it back, at least with no interest to your mom maybe. But you have to somehow recover that capital. And when you do that using any number that's reasonable in the industry, you magically get a number on how much money you can spend per watt. That's when you build your box, it has a dollars per watt price to it. It's about 2 or so times 1 minus the ratio of how much the cost of making your energy is divided by the product price. And that's pretty close to what it needs to be. You can quibble with a factor of 2, but not very much. And that's really basic economics that everyone who does economics knows. So magically, if you go and look and see what we use, like coal plants and power plants and oil refineries, they all come in that bound of around $1 or so a watt. And that's just a result of economics. That's why people who build these things don't need to get subsidies to do it, because they can fit within that economic bound. They pay back a reasonable return on capital, and so you can build them. And depending on how you price different kinds of technologies, they all have to fall within this little magic range. Now, how can we do this, what we do today, which works economically, and science and engineering has given society a way of doing that? How can we do it in a environmentally sustainable way? Well, one thing that works is wind. We know that wind can be priced at 50 cents a watt, so that's well within the bound. And if you can put some batteries with it to make it so it's a little bit more deliverable, that ends up working economically. But whether or not that will be able to provide the 30 terawatts or so that we need by 2050, that's hard to imagine. So we go back to solar, the topic of this conversation. What we're trying to do is figure out a way of using the 200 watts per meter squared, which is the average amount of sunlight landing on any square meter per day, average, and how to convert certain inputs and certain outputs and make all this work with some kind of reasonable economic balance, if you will. And we don't even have to have profit. It just has to be a little bit more than 0 so you don't have loss. Ideally, that would be greater than 0 by a fair amount so you can get people to buy into it who want to make money. But even if it's just slightly greater than 0, you're okay. So how do we do it? If you look at how all solar processes work, no matter what they are, including the wind and hydro, the photons absorbed. Photons only get absorbed one way. They make electrons in holes, or electronic excitations. And once they do that, oftentimes they'll relax and make vibrations that are heat, and we use that for making winds. We use that for evaporating water to make the hydraulic cycle, and people now use that to convert solar energy into electricity by turning turbines. So converting the electron hole pairs, which are the electric excitation, into thermal energy is relatively straightforward and easy to understand. So our box can do that. Alternatively, if we capture earlier on the electrons in holes, we can make photovoltaics. So if we capture that electronic excitation and separate the charge, we can make a photovoltaic. Or what I'll talk about a little bit today is if we take those electrons and holes and make use of them in electrochemistry reactors, we can do photosynthesis. And plants do that all the time with exactly the same methodology to make biomass. So this is how we're going to use the radiation. Now, the Earth itself does a pretty decent job at some of these things. For example, out of our 120,000 terawatts of absorbed sunlight, we can make 1% of that into wind. And so that's a solar to mechanical conversion that does okay. It can make 10% of it into, if you look at the hydraulic cycle, it's a huge amount of water that we circulate into the atmosphere. Enormous amount of that initial energy is captured by moving that water around. And then it makes biomass and other things. So the Earth is itself a conversion system. And one of the things that for the people in a different generation than me need to think about is different ways of building reactors that take advantage of large, enormous scales. If you're going to use solar, it has to be on enormous scales. And the things that work all have gigantic reactors. They're taking advantage of the entire Earth. They're not taking advantage of a little 1 meter by 1 meter panel. So these hydroelectric wind has worked. It's market proven. And there isn't any doubt that many applications these can hold on their own without any subsidies. Now, why is it that agriculture works? That also has been proven through centuries of activity, and even in non-subsidized markets, people can make money farming. Even though the efficiency of solar to biomass conversion is about 0.1%. So if you think about it, you have 200 watts per meter squared. That's all you get. 0.1% efficiency means that for every meter squared, you're getting 0.2 joules per second, and you're trying to make products worth the same as gasoline and fuel, around $10 to $20 a gigajoule. And what that means is that for every square meter that you have of agricultural land, you're only making 10 cents. That's your profit. So 10 cents per meter squared. Now, why does it work? It's because farmers can farm that meter squared for less than 10 cents a year. And that's how they make money. And it's only because they don't need to produce very much of it, because with only 0.1% efficiency, you would need land areas that are enormous to produce any more than what we need to eat, which is only about 200 watts per person, which is not very much energy. We use about 10 kilowatts per person in all the other things that we do. But just eating, we're only 200 watts, so that's pretty easy to sustain over small areas. Now, why solar to electricity conversion does not work? It doesn't work for, in some ways, the same argument. Now you have 10% efficiency usually. You could have 12, 13 maybe if you're lucky. You're producing electricity which has a value of around $15 a gigajoule. And when you look at that, that's only $10 per meter squared per year you're making. Now, who's going to spend $500 to make something or install it that you're only going to make $10 on? That makes no sense at all. Nobody would do that. And that's as simple as it gets of why it doesn't work. It's too expensive. It would be great if it was cheaper, but it's not. And in fact, for people who are honest, when you look at the prices of the modules, even though in this room I've heard people talk about how it's exponentially getting smaller, in fact, the reality is they aren't getting smaller. They're about pretty stable since about 2007 when you look at the installed cost and the true module cost and everything. So it's very unlikely that they're going to get down to a number that where this is going to make sense. And one of the reasons for that is because besides just the crystal and the semiconductor portion itself, these things have to be put out in the real world. And it's not always a nice sunny day where these things are going to be. They're in all kinds of environments. And the way you stabilize a structure in a harsh environment is expensive. And anyone who's built a house where you have to just install a window, window's pretty simple. But by the time you install it and you put it in so it's stable, in case of a big wind, it costs a lot more money. And that's exactly the case. And in fact, when you look at things that we make in large areas, something as simple as 1 inch of concrete costs a fair amount of money per square meter by the time you put it in and you have the guy come and smooth it out and you do all the other things that you do. Everything that needs to be stable for long periods of time on a square meter basis costs some money. And it's very difficult to see how you can get a solar cell that has electronic connectivity cheaper than an asphalt road. It's a very tough thing. It could be, but these are just comparisons. But the reality is that there's nothing that we make in large areas on Earth that can be made as it needs to be. So if they were 100% efficient, you could spend $400 per meter squared. If they're 10% efficient, you can only spend 40. So these things become very prohibitive. In spite of that, people have shown these exponential growths in solar installations. And so why is this? How is this consistent with what I'm just saying? If it's not such a good idea, why is it that everyone says it's taking off and we're going to see solar panels in everyone's houses? Well, Google, for example, was talking about grid parity in 3 to 4 years when they first talked about their solar conversion pathway. Well, it turns out when Google took a closer look, Google installed a large number of panels on their sites. They did careful analyses of what happens. And when they did that, they started to learn about the real world of solar energy. For example, it varies significantly as a function of when the year is, or what part of the year. From winter to summer, you might lose 50 to 60% of the energy. If you look at just simply dirty windows and then clean them, you can double the output. So lots of real things happen in solar panels when you really use them in duty. And Google learned this. And as a matter of fact, they are now out of the solar business for many reasons, not just the reasons that I've mentioned, but there's many reasons they got out. But then many other people are leaving this area because they don't see the economics making any sense. One of the other things that one can analyze when you analyze this exponential growth is who did it. For example, in 2008, almost the entire growth in the industry was from sales in Spain. Well, if anyone's read the newspaper recently to find out what's going on with Spain, you can figure out how wisely they spend their money. So the fact is that just a few countries, Germany and Spain in particular, have dominated where people are buying the panels, and where they're selling them from has been an interesting change as well, because whereas they buy most of them in Spain and China, they make almost the vast majority of them now in China, and in fact China doesn't use very many of them. China uses coal. So very wealthy countries can't afford to use expensive renewables, primarily because people like Germany and the US, they use a lot of coal. So they can balance a very expensive, non-economical energy source with something that's very cheap, and coal is very cheap. So what we have to do is be able to provide people with an economical option that gives them a choice of choosing a solar technology that will compete with oil and coal on a real basis, not on a phony basis. Interestingly, the subsidies, we all think that the US and their Solyndra loan guarantee was the worst and the most egregious case, but China's doing the same thing. China's subsidizing their solar production as well, and they're capturing the production in China and using our taxpayer dollars to go to China to buy them. So it's a really disastrous situation because our subsidies here are generating cash for China, which is then in turn subsidizing it to make it grow larger and larger there. It's not sustainable. The cost reductions, by the way, in the last decade have really come from the fact that we've moved production from the US or other countries that were expensive into China. So the reduction in the panels and module costs have largely come from displacing higher cost workers with lower cost workers, not because the technology has gotten any better. I mean, the cells themselves have gotten a little bit better, but the rest of the package has not. From the DOE, they look at the levelized cost of producing electricity, and if you believe the DOE, if you look at, and they're pretty optimistic about solar, the numbers are about 3 to 4 times what you would be producing electricity from by natural gas based on 2009 numbers. They're different now because gas is a little bit cheaper. So these numbers would be even less favorable for solar. So it just doesn't compete in any real way. Now, in this room, again, I've heard a lot of people talk about the advances in photovoltaics over the decades. Well, in fact, the first cell was about 1 to 2% efficient using selenium, and that was more than 100 years ago. So in fact, the first cells weren't so bad. The Adams and Day cell wasn't the worst cell in the world. And in more than 100 years of development, it really hasn't gone that far. It's not been Moore's law. It's been, it's been okay, but it hasn't been something to write home about. And there's nothing really in commercial production that is significant in terms of our energy production. So I want to talk about solar to chemical because I don't believe that solar to electric has an economic chance. Now, why solar to chemical might? It's because it overcomes a lot of the problems with solar to electric, because the solar to electric needs wires, and it needs to be in a structure that sustains environmental challenges, whereas when you make photons or use photons to make chemicals, you can relax a lot of the system requirements. And so you're still going to have an excited electron-hole pair, but rather than using those to make electricity, we can immediately transfer those to make chemicals. And those are easier to store, and the structure can potentially be a lot simpler. This is what plants do. Plants will absorb the light. They'll make oxygen, and with the reducing potential, they'll make things like sugars. And so you can do this quite well, and the sugars build up in the plant, and then you can harvest them when you feel like it. So you have built-in energy storage in a solar to chemical photosynthetic process. And this is what JCAP, this DOE Solar Energy Hub, is trying to do. And what they'd like to do is make oxygen and hydrogen as the products of this photosynthetic process. So how does photosynthesis do economically? Well, here's the ethanol production in the US. Again, that great exponential curve, which gets everyone excited who are investors, and you think it's going to be the greatest thing since sliced bread. But in fact, we know that the only reason it rose like that was because we mandated that 10% of the gasoline use it. And as soon as it gets to that number, it will stop growing. So even though the exponential generates lots and lots of investment dollars, in fact, this was constrained by unsustainable economics paid for by the taxpayers, much like the case of the solar cells. Biodiesel is the same way. Lots of economic excitement because of this exponential growth. And in fact, the production in the US is going down with biodiesel because the economics are unsustainable. The price of the feedstock for biodiesel skyrocketed. So natural photosynthetic processes don't make economic sense beyond a certain relatively small number. Now, what about beating nature and doing artificial photosynthesis, which is what I believe has the only chance, and I would say chance, not guarantee, of making any sense? This has been worked on also for a long time, and this is a picture of Giacomo Chamichan, an Italian photochemist, on top of his laboratory. And what he was trying to do in all these flasks out in the sunlight was to convert chemicals from one type into another using sunlight. So he was quite interested in displacing coal as the fuel of choice for the time, because he was concerned about coal. Now, people have tried to do this for a long time, just like they have with photovoltaics, and there's been lots of industrial involvement. For example, the GE was involved building systems that use cerium, absorbing ultraviolet light to make hydrogen and oxygen, much like people are trying to do again today. The basic process that most people are working on, which is similar to what we're interested in, is taking the electron hole pair and capturing it in a semiconductor device so we can separate the electron in the hole and make use of the electron to do reduction chemistry and the hole to do oxidation chemistry. And this was demonstrated in a very famous paper in 1972 by Fukushima and Honda, who did this with titanium dioxide. And this generated all kinds of excitement. And unfortunately, it's also generated a mindset that the way we need to do this is with photoelectrodes, oftentimes using TiO2, because TiO2 works so well with ultraviolet light. There's been other systems that have been proposed here. They basically took a photovoltaic, so this is just a regular photovoltaic device. They covered it around with an insulator, and they floated it around in a little bath. And from that, the surfaces of that photovoltaic, they made, in this case, hydrogen and bromine. So you can make chemicals using the photovoltaic as the absorber, and it doesn't have to be built into an electronic system. And they recognized early that removing the wires and the need to interconnect the electronic devices could get the cost down significantly. So now the system is a lot easier, plus you have built-in energy storage in the form of the chemical products. So much like with photovoltaics, we've had 100 years of time to work on it. Lots and lots of work was done in the 1980s. They've shown beautiful physics devices that have multi-layers. They can absorb any layer band of the sunlight that they like. They can do extremely sophisticated multi-layer structures, and they can make hydrogen and oxygen, and they can make other things. It's all been demonstrated, up to nearly the theoretical efficiency limit. And yet today, the only thing we have in the commercial sector is a TiO2 mosquito trap and an air purifier. So all that work with really no commercial outcome, in spite of an enormous amount of money put in it. So I want to talk about tactics, because if you want to do the right thing, and I think the right thing is try to find a cost-effective way to make use of solar energy. One way you can do it to go forward and have other people pay for it is to scare them. We scare them in saying that the sky is falling and we have an energy crisis and we have to do something. And that's been one of the approaches. Or we can keep making promises about how photovoltaics, the price is going to come down no matter what we do, and it's going to bottom out. We just need to build more facilities and give more cylinder money out there. That's another promise that's impossible to keep because that structure is not viable. Or we can create options that if we solve some problems, they can ultimately result in an economically sustainable system. And that's really what academia should be working on. We shouldn't be trying to mass-produce solar panels in fabs using conventional technology. We should be figuring out a completely different structure because the existing structures won't work. What's happened, I think, in the field is these are great experiments for the lab. They'll find some device that works beautifully, highly efficient. They understand it. They'll do all kinds of fancy characterization on it. And then they'll say, aha, let's try to put this into a system that works. And that's really been how the field has evolved. They've taken very highly efficient structures, such as the ones they use in satellites, and they reconfigured them to put into electrolyte systems that have very high efficiency oftentimes, but they just make no sense. They didn't make any sense as a photovoltaic commercially, and they certainly don't make any sense as a photoelectrochemical system. So this is the way that historically the field has evolved. All these conceptual process models that have been built around existing photoelectrode structures all fail. They don't make any economic sense because they're basically a photovoltaic, which doesn't make economic sense on its own right, plus an electrolyzer, which also doesn't make any sense if you couple them together because the efficiency is the product of the two. And so you have an overall less efficient process that costs a lot more. So it just doesn't work. So rather than doing thinking that way, instead of starting with a very exotic system, why don't we design a process that if it works, the material will result in an economically viable system. And that's really the approach that we take. So you have to go back to nature. We know that agriculture works. We know that even with such a crummy efficiency of 0.1%, people can sell food economically sustainably. And with algae, that's the approach that they're taking with algae. The only problem is their efficiency isn't a lot better than corn or wheat or rice, and so you still need these enormous areas and large amounts of water that make it not particularly viable. If instead you replace the algae or the plant with a synthetic particle, for example, and you can get the efficiency up to 10%, you can ask the question, well, if I have that technical advance, can it work? Will it make any sense? So you go back to an engineering process model, and the ones that we've looked at include these very simple slurry reactors, much like the algae floating around in a pond, so that's cheap, but it now has artificial particles in there that do photoelectrochemistry. Now people have looked at this, and there was a very nice study, Brian James and his colleagues at Directed Technologies, which is an engineering firm that does contract work for DOE, and they looked at these different photoelectrochemical processes. They looked at the photoelectrodes, they looked at these slurry reactors, and it turns out that the only one that makes any economic sense at all is to take basically a baggie and put it on a large area like this, filled with particles, and collect the product in the gas phase. If you do that, you can make hydrogen at a price point that makes it make some sense. And here's just an analysis of the various types that they looked at. And the one that wins is the very simple single gap photoelectrode sitting in a solution. That one, if it works, might at least, on paper, make a system that's sustainable. But that's the only one. When they've done the same analysis to every other kind of photocatalytic or photovoltaic system, none of them come in with any economically viable outcome. And this assumes that there's a stable, 10% efficient slurry material. So it assumed that in the model. So now you can go back to the lab and try to create that. So how can we do better than nature? Nature's at 1%. We want to take our synthetic particle and do better than 1% at absorbing the light and creating electron acceptor, electron donor pairs. And many different approaches have been taken. There's groups that work on homogeneous photocatalysts where they use basically the same kinds of pigments that are in chlorophyll to absorb the light and split the charge. That's the basic function of this molecule. It needs a large enough electric field to absorb the light and split the electron in the hole off to different regions where they can do different chemistries. We're working on inorganic particles, but not to say that they're any more efficient or better fundamentally. They're not. Whichever one's cheaper wins. And we believe that this one will be cheaper. So our approach is to use inorganic particles. What we want to do is try to use theory to improve low-cost semiconductor materials that will absorb the light in the visible spectrum at a gap, where the band gap is such to optimally absorb the light, transfer the electron in the hole out to sites where they can do electrochemistry, and then do that electrochemistry as efficiently as we can. There's also issues of how you include barriers here to prevent the reaction of the products on one electrode with the other, and that's a detail I won't talk about right now. But there's other parts of design. But there's no fundamental reason why you can't make this artificial cell, if you will, cheap and efficient. There's no fundamental blockade. And the nice thing about these particles floating around in a baggie is they don't have to be electrically connected to one another, and they're incredibly fault tolerant. So if one doesn't work in a collection of a bunch of them, it doesn't ruin your system, whereas you short circuit your photovoltaic, well, part of it, then it ends up causing bigger problems. And you can also recycle these things through the system. So the system ended up being fairly resilient. You can do this also in macroporous or microporous systems as well. There's lots of fundamentals that can be done in these kinds of systems. So our approach in our lab has been to identify cost-effective materials with a gap of approximately 1 eV and an internal quantum efficiency greater than 90%. If we do that, at least we have a shot at getting to the final 10% efficiency that we need to make this viable. Once we do that, and not until we do that, I almost don't care what the chemistry is going to be. All I need to know is I want about 1 eV, just like with photovoltaics, you want about 1 eV because that's the best place to absorb the most of the solar spectrum. So I'm choosing that for efficiency purposes, and then I'm going to select what chemistry I'm going to do. And one of the ruts I think that the field has gotten into is they've always assumed that they want to split water. So they're going to make hydrogen and they're going to make oxygen. And they've built that into as a constraint, which isn't really what you want to do. What you want to do is say, can I absorb the light efficiently, and then I'll choose the reaction that makes the most sense and it makes the most economic sense for me in that particular location. So and there's lots and lots and lots of redox chemistry one could do. So once we do this, we'll select the redox chemistry, and I'll show you some examples in a second. And then we're going to go and we're going to maximize the kinetics at the catalytic site. So here, this has to do with electrocatalysis. Now, fortunately, most of the reactions that we're looking at are very fast. Making hydrogen is kinetically very quick, and most of the reactions that we're looking at, such as making bromine from bromine ion, are also very fast. So we don't have too much of a problem with the kinetics, but we do have a lot of problems with the stabilization of the material in a large electrolyte system for long periods of time. And so we have to figure out ways of doing that. So I'm not going to talk in great detail about the details of the methodology, but just simply to say that we use high throughput methods to look at lots and lots of semiconductor materials to try to find those that will perform in this limited design constraint. Now, we started out this work by looking at known hosts, the ones that other people had published, and tried to make those more efficient. This ended up being a mistake in retrospect because we chose the oxide of the day, tungsten oxide, zinc oxide, and we looked at copper oxide, mainly because everybody else was looking at them. And what we found, like other people have found, is when you can play around with tungsten oxide and you can improve the properties of tungsten oxide by coupling theory with experiment to try to change the semiconducting properties of the oxide. Same thing with zinc, and lots of people have done work on zinc, including at this institution. You can put dopants in there to make it absorb better in the visible. And we did a lot of that work and showed that we can make a more efficient zinc oxide, we can make a more efficient tungsten oxide, and we can make a more efficient copper oxide. None of them work well enough, and all these numbers here, I won't dwell on them, but they're all tiny. None of them come close to the 10% efficiency that's needed. And there's lots of interesting science that one can do on these things, and we made the mistake of falling into that rut of saying, okay, well, let's really study the cobalt properties inside of zinc oxide, and we spent a lot of time doing that. And unfortunately, at the end of the day, all we had was a bad semiconductor that worked a little bit better than the worst one. And though we did learn a lot about zinc oxide. Tungsten oxide, the same thing. We made better tungsten oxides than had been made before, especially when we doped in moly. But the fact is that it's still not even close enough to the goal to make any sense. And we shouldn't really have started with oxides because they have too wide of a band gap to start with. One of the materials that we worked on a lot, more than I would like to think, was zinc oxide, iron oxide. And iron oxide is intriguing because it's safe, you can eat it, it's abundant, it's super cheap, it's red, so at least it has a color that starts off looking pretty good. The problem is that it's fundamentally a bad semiconductor. It's a Mott insulator, so it has all kinds of difficulty in having a polaron move through the lattice and splitting the electron in a hole. It's got anisotropic conductivity. In some directions, it's horrible. And it doesn't have a particularly electrically catalytically active surface. So it has all kinds of fundamental problems. Nonetheless, we persevered. And this is some work we did showing that we could use theory. And this I think is something that's transferable to better semiconductors. We could use theory to at least tell us, when we put in different dopants, we could tell in advance what it might do to the conductivity. And it did, in fact, show us that we could make terrible iron oxide a little tiny bit better by putting platinum, chromium, and aluminum in for different reasons. The aluminum strains the lattice, so it kind of pretends like it's expanding, putting pressure on it, and that causes improvement or reduction in the effective mass of the carriers. We could break the insulator boundary by building mesostructures. We could break some of the symmetries. So we can always make it better, but not close enough to what it needed to be to make a good semiconductor. And so you can see, even for fairly bad performing pure iron oxide, with playing around with some dopants of aluminum in this case, we can improve the properties enough to write interesting papers about it, but not enough to get even close to what we need, which is a 10% IPCE, incident photon conversion efficiency, across the visible. And the iron oxide just doesn't do it. And I don't believe it can ever do it. We looked at de la phosites. I won't talk about those in detail. Those were predicted first by theorists who told us those would be good things to look at. And so we were very optimistic about them. And they were, in fact, very good absorbers. They were terrible in terms of their efficiency, though. And so none of them worked very well. And I won't talk about the details. Phosphides, we think, are worth a lot of work. And we've had some very good work with, certainly indium phosphides are well known as an efficient semiconductor. We've made other phosphides. And what you notice right off the bat with your eye, your eye spectrometer, you can tell that those do have a gap somewhere where you want it. At least they're absorbing strongly in the visible. And that's really the color that you want for a good photocatalyst. The problem is that they're very unstable. So we have to encapsulate these things with stabilizing oxides to make them stable in this milieu of electrolyte. Sulfides also, same thing. They're much better semiconductors at T equals 0 than any of the oxides. And those are having very good luck, except they're also having stability problems. So one point that I want to make, because there are people in the audience I know that are working on photocatalysts, is I think that there is no evidence whatsoever to support working on wide gap oxides. I think there's no hope for those to ever make the 10% efficiency that you need in the spectrum. I think that they, in fact, if I ever review grants on them, I reject them. It's just the way it is. There's been so much work on TiO2, none of which has a prayer of being effective as an absorber. TiO2 as an electron conductor, not so bad if you're going to use something else to functionalize it. But TiO2 as the primary absorber, I don't care what you put in the lattice, isn't going to work. The other oxides also very difficult. The only oxide that we thought had a hope was iron oxide. I don't believe, certainly in our hands, we can't make it good enough. Probably the last hope is copper oxide, and we haven't done enough to say one way or the other whether it will ultimately pan out. Our feeling is that sulfides and phosphides deserve a lot more attention. They're abundant, most of them. They're very cheap in principle. And of course, silicon is still something that can be used if you're only going to be using a band gap of 1. So silicon's quite important. Most of our structures structures that we imagine putting these semiconductors in are all in the same kind of schematic form that I showed you, where we have a semiconductor particle, electrocatalysts to form the cathode and the anode, and then some kind of an encapsulating oxide, either to protect the electrode from back reaction or to protect the semiconductor from from degradation. I'm not going to talk about the development of electrocatalysts because I don't have a lot of time for that, but suffice it to say that you can do a lot with electrocatalysts, but you need to know what the reaction is that you're going to do. One of the questions that frequently comes up is, what do you want to use for your chemical potential product. I mean, how do you want to store the photon energy? Now, most everybody wants to make hydrogen, including us. And the reason we like making hydrogen is because it's very fast to make electrochemically, and it's easily separable. It can be separated out of solution very, very simply. For the electron donor, for the hole, you want to really avoid zero-value products. Oxygen is basically a zero-value product. If you're going to go to all that effort to collect the photon, split the charge, and make products, why do you want to make something that you can't sell to anyone? Oxygen, nobody wants oxygen. So you have hydrogen, which is good. You can make lots of things out of it. You can make methane out of it. But oxygen, you've gone to a lot of work to make something that isn't very valuable. There aren't very many things you can make by oxidation that are valuable. Halogens are really the one thing that comes to mind, and that's bromine and chlorine, or iodine. Iodine is more difficult to make a case for. But bromine and chlorine are the only two products of oxidation. Alternatively, you can take things like wastewater and oxidize the wastewater. So something that you're doing is taking a negative value product and making it less negative value. So that's the only things that I can think of that have value in oxidation. So, but you want to avoid the zero value products. I'm not going to talk about that work. Let me skip through some of this. So how do you make these designs end up being, so that they're stable in electrolyte? This is some work that here at Santa Barbara, Galen Stuckey, Martin Moskowitz, and some of the postdocs working with them have developed a means of putting these semiconducting devices inside of aluminum membranes. So you can build up a full, if you will, effective photovoltaic panel that's now a photochemical panel, where they've installed the absorber and the electrodes, where they put the catalysts on the poles. And in this system, you could in fact do all of the photoelectrochemistry with autonomous units. So each one of these little photoelectrochemical reactors itself a autonomous unit. And this work has now reached fruition, where they've actually made these with cadmium selenide. Nickel oxide is the cathode and gold anodes, and they're now in the process of testing that. So this would be a way of making these things very inexpensively, so that they're encapsulated, protected from the environment, and you can put a highly efficient semiconductor in the center. I'm not so sure that cadmium is one that we want to have there, but nonetheless the process is clear. Now, I want to just say a few words before I stop on the concepts of integrated systems. One of the things that people have done a lot in the biofuels and the renewables area is they've imagined their biodiesel plant or their cellulosic ethanol plant in isolation. And here's a picture this is from Ventura, in fact. This is one of the early refineries. And when oil cost nothing, basically, it just kind of came out of the ground, you could live with a single-purpose chemical plant where all you made was a very low yield of gasoline, because the feedstock didn't cost you anything and the capital was minimal. Nowadays, though, because the feedstock isn't minimal, the price of oil is pretty high, a modern refinery has all kinds of integration. It doesn't just make gasoline. It makes chemicals. It makes lots of other things that make the overall process economical. If you just made gasoline in a refinery, you wouldn't make any money. You've got to sell the other things. And so the idea that you have a integrated plant of some kind must be brought into the discussion when you're going to have any kind of a solar facility as well. It's not going to just be a single-purpose plant, or else it probably won't make money because fuels are so cheap. So one alternative is to combine it with wastewater treatment. So if you were going to have a wastewater stream, you do some treatment and separation, and then you take the oxidating potential polyols that come out of the organics in the waste stream, and you use a photoreactor to oxidize those, and in the process you make hydrogen and not necessarily CO2, but further oxidized wastewater products. And this kind of an integrated facility gives you the value of treating the wastewater, but also the value of the product. And it's a lot easier to oxidize these wastewater products than it is to oxidize water to make hydrogen and oxygen, and you're not making the oxygen which was the zero value product. Some work that was done by John Turner at NREL back in the 1990s showed that you could take hydrogen and bromine and make bromine, so a very valuable halogen and hydrogen at a much lower voltage than you can to make hydrogen and oxygen. And that same concept was captured in a Texas Instruments device where they made bromine and hydrogen and ran it through a regenerable fuel cell. The bromine was easy to store because it's liquid at room temperature, and the hydrogen worked very well in the reversible fuel cell that they had as a commercial prototype. So this idea of making something other than oxygen that's easier to store and transport has been at least looked at by serious commercial vendors. Here's an example of where you might integrate the process. There's a process if you take biomass and make biomethane in an anaerobic digester. This methane can be made into gasoline through a chemical process that has hydrogen bromide as a byproduct. This process is too expensive to work commercially because of this very expensive hydrogen bromine water oxidation. But if you coupled that hydrogen bromine oxidation with a photochemical process where you converted the HBr to hydrogen bromide, you can reduce the cost of the continuous methane to gasoline plant, and then you can also get hydrogen. So you're going to get hydrogen at a much lower cost than if you tried to do this with water, and now you have a much more valuable product, which is the bromine. So the idea is the same. Couple the solar process with something else. So I'm going to stop here and summarize. Today, there are no significant cost-effective man-made solar conversion processes, man-made being the non-agricultural processes, because there's no sufficient, efficient, stable, scalable, and cost-effective absorbing material. That's just a fact. I think that we're on the verge of having theory and material science be able to help, and if there's any chance at all, to make a very cheap and efficient photoelectrochemical microreactor, if you will. How you apply that is probably not going to be for water splitting. I think water splitting is a rut that the field has fallen into because it sounds so good. You know, we're going to take water and we're going to split it and we'll make hydrogen and oxygen and everyone's fine. But I don't think cost effectively you're ever going to accomplish that because the oxygen evolution reaction is so energetically costly. The system really makes a big difference, and you have to think about that up front before you start one of these things. Fundamentally, the production of fuels and chemicals at $15 a gigajoule is possible, but it's going to be very, very difficult. And I think that the time has come to ignore, in many ways, or at least question the way the field and the so-called experts have gone for so many decades and step out of the rut of photoelectrodes that look just like photovoltaics and try to do something else. And I think that's the message I want to convey to the young people, that that's where you have to go. So I'll stop there and take questions. Well, he said, what's the prospects of perovskite solar cell that is out in the literature? Frankly, I don't know which one you're talking about.
These ferroelectric, films, have you seen reports of those?
I have, and I guess my comment is that the ultimate relationship between efficiency and cost has no interest in how you made the square meter material. So even if it was free, if the cost of the stuff that you put down was free, if you're going to configure it in a standard photovoltaic architecture that needs to be placed in a superstructure with electronics and all the other things that go into it, I think it's very difficult to make that work, even if the material is free. But I'd be interested to see their numbers.
What are the synthetic challenges for sulfides? I mean, I know a lot of people have run into them.
I think that it changes so quickly. Every time that people say you can't make something using wet chemical techniques, someone shows that you can. So people have said that you couldn't make lots of things. I've seen people make germanium in an electrochemical deposition that was highly efficient. Now, who would have thought that was possible? So I remain, until they can show me theoretically why you can't make it using a relatively inexpensive synthesis route, I would say I'm open to seeing a reason why it can't be made. Synthetic guys do amazing things all the time.
I have a question about the economics that you emphasize so much. If you are successful in creating hydrogen, eventually you burn it and you get energy, right? I know that this country is flush with gas. So how, and it's not catching up. So can you comment on that?
I think that there's almost no chance you're going to beat the price of natural gas for decades. I think that's impossible. If $4 a million BTU, which is what, or $4 a gigajoule, which is roughly what it is, it's impossible. Probably $8 a gigajoule is probably also impossible to make it by any synthetic means. But once that happens, remember, 10 years ago it was $10 a gigajoule. So natural gas prices have fluctuated. And the thing about shale gas is that it depletes very quickly. So we're going to have lots of gas in the next 10 years. We're going to have tons and tons of gas in this country, and then it's going to run out very quickly. So if we produce gas here, which I think we should, there's no point in deploying these things tomorrow. But what happens when the gas runs out?
Right.
Which it will.
So how many years do you think the gas can sustain the...
It depends. I mean, I think that I was just up in North Dakota a few weeks ago, and the drillers told me every time they drill the hole, they find more gas. So if you believe, that's an anecdote. But nonetheless, it seems like there's a lot of gas there. Every report that I've ever seen says there's a lot of gas. So you're not going to beat that price unless there's a carbon tax, which is very unlikely. So as long as we have abundant natural gas, none of this is useful for making hydrogen. But that won't always be the case. And that's, I think, all of this is for the future. Our generation is going to be fine burning oil, frankly.
If you make hydrogen, do you compete with syngas? I mean, with the current way of making hydrogen, can you sell it cheaper than what we have now?
If you can make it, if
by, let's say, from HBR.
they use hydrogen for, say, making ammonia, they have to
make ammonia, you can make methanol, you can make a lot of things. But the question is it cheaper than using it by making methane?
Methane at $4 a million BTU, which is what it is today, you can't beat that. It's impossible. With any kind of solar technology, it's just even if the box is almost free, by the time you separate it, you collect it, you compress it, $4 a gigajoule is so cheap that it's very tough to beat that. I don't see how you could beat that. I think people need to be realistic about that also. If gas is cheap, you're going to use gas. I mean, it just doesn't make any sense not to. But one has to also remember that there is a limited amount of hydrocarbon in the planet. So in 50 years, if you started working on these kinds of problems, it would take you another 50 years to solve them. And so you don't want to be up against the wall. It's much better to do the work today so that when the gas runs out, and it will, you have an option.
What happens to your numbers if you do put a carbon tax in?
Depends on how high the carbon tax is.
Well,
If it's $15 a ton, it doesn't do much.
15, how about 50?
50, you start to feel it, but it won't make PV cost effective. It'll make, and remember, gas pays less of a carbon tax than coal. So coal will be hit differentially more than gas. And you can take a pretty good hit in gas and still be cheap. As long as it's 4, if it's 10, then it becomes a bigger problem. But at 4, you can take a pretty big, you could put a big $100 a ton probably, and you would still be cheaper than photovoltaics. And no one's going to put a $100 a ton CO2 tax in. I don't think I think if you have any at all, that would be amazing.
A lot of the processes we were most optimistic about ultimately produce hydrogen, but storing and transporting hydrogen is notoriously really difficult. So,
Absolutely.
I mean, how do you get along?
You immediately convert it into methane. Making hydrogen reacting hydrogen with CO2, for example, you can make methane easily, a high conversion, and put it in the pipeline. We have, I think it's 26 million miles of natural gas pipeline already in the U.S., and something like that. And it goes everywhere. Everyone's home has a spigot, or most people's home has a spigot already. Put it in the pipeline.
Speaking of that, so do you know when it's going to become cost effective not to burn hundreds of tons or thousands of tons of natural gas at every refinery? I mean, every oil field has a huge, but even just drive down here on the 101 and you look up to the left and there's this flame going 24 hours a day.
Well, right now in the Earth, of our known reserves, we have roughly the same amount of gas as oil known. So there's going to be a lot of gas around for a long time.
No, but I'm asking, why isn't that being stored, collected?
Because because most of the places where you see the flares, their primary purpose is to drill for oil. and you get about 10% of the carbon comes up as gas. If your primary purpose is oil and they're charging, you're getting $140 a barrel for the oil, your interest in the gas is minimal. The only reason they don't flare, the reason they flare it now for two reasons. One is safety, and the other is they don't have any place to put it. If they could put it someplace, and they're trying to build pipelines, but people don't like pipelines, they would put it in a pipeline. All these, the platforms here in the channel, they all have gas pipelines, and the only reason you see a flare around here is when there's an emergency or some unpredicted transient. They want to get the money for the gas, and they put it in the pipeline. So here, we don't really flare any. In North Dakota today, they're flaring, I think, 100 million standard cubic feet a day. In the Middle East, it's like a fire. Russia, they're flaring it like crazy because they want the oil. Gas is just too cheap, and the expense of making liquefied natural gas is so high, they have no option. You have to use the gas locally. If there was a gas to liquids technology, again, a challenge for the chemists here in the group, if you could convert that methane into anything, it doesn't almost matter what it is, anything that you can ship that's cheaper than gas, then you win. And many people here have worked on that problem. It's a tough, as you know, it's a tough problem. How do you react methane with anything? But if that's what they need a gas to liquids technology that doesn't cost the cost of the current gas to liquids technologies.
Your photochemical process creating hydrogen, is that been lab tested, your baggy system and so forth? Does that exist? Forget about combining with CO2 to create methane. Just creating the hydrogen.
We weren't the first ones to do that. That's been you can take TiO2 and in 20 minutes with a UV lamp, you can see hydrogen and oxygen in your baggie. So that in itself isn't particularly novel. The real advance that somebody, hopefully in this room, will make is that if they could take and have an efficiency of 10% for visible band sunlight. Nobody's done that. So the idea of making hydrogen and oxygen on particulate photocatalysts has been known for decades. And you could do it this afternoon or tomorrow. But the real challenge that we don't have the answer to is how to do that at 10% efficiency and have the cost of the materials and the particles be low enough to beat the price points. And that's why in some ways it's no longer a physics problem. I mean, we know the physics. There's some tricky details at interfaces that one has to deal with, but the basic principles are known. It's a matter of finding materials with directed searches using known theory, and then engineering a system that makes cost sense.
Thank you. Okay, let's thank Eric for a very